Dark plumes rising from a remote stretch of ocean north of Papua New Guinea have drawn renewed attention to one of the least understood volcanic regions on Earth. Satellite imagery captured during the second week of May revealed steam columns, floating pumice, discolored seawater, and intense thermal signatures erupting from beneath the surface of the Bismarck Sea. Seismic tremors were detected first. Then came the expanding patches of green and gray water, followed by ash-rich plumes punching through cloud cover and drifting across the Pacific skies. The eruption appeared without warning in an area where even modern ocean floor maps remain incomplete. Beneath those waters lies a maze of ridges, spreading centers, volcanic cones, fractures, and tectonic collision zones that scientists are still struggling to fully chart. The questions surrounding the eruption have become increasingly urgent. How shallow is the vent? How much magma is rising beneath the seafloor? Is this simply another short-lived submarine eruption, or the beginning of something far more dangerous? And perhaps most unsettling of all, could the same chain of geological processes that unleashed the catastrophic 2022 Tonga-Style eruption disaster now be developing beneath the waters of the western Pacific once again? The eruption site is believed to lie along Titan Ridge, an underwater volcanic structure roughly 16 kilometers, or 10 miles, southeast of a submarine eruption recorded in 1972. Satellite observations from NASA Earth Observatory showed tightly clustered vents breaking through the ocean's surface beginning on May 8th. Within days, multiple Earth-observing satellites detected strong heat signatures spread across approximately 7 square kilometers, or nearly 2.7 square miles. Floating pumice rafts drifted southwest while white steam plumes rose high above the water. Authorities in Papua New Guinea quickly issued maritime warnings about turbulent currents, falling ash, unpredictable swells, and possible tsunami hazards near the eruption zone. The concern was not merely local. Underwater volcanoes possess the ability to transfer enormous amounts of energy into the ocean with very little warning, especially when seawater interacts violently with ascending magma. The eruption immediately invited comparisons to Tonga because the mechanisms unfolding beneath the sea share several unsettling similarities with the processes observed before the catastrophic explosion in January of 2022. In that event, a submarine volcano located within the Tonga-Kermadec volcanic arc erupted with extraordinary force, producing one of the largest atmospheric explosions ever recorded by modern scientific instruments. Tsunami waves spread across the Pacific Ocean, damaging coastlines thousands of kilometers away. Ash clouds climbed approximately 58 kilometers, or 38 miles, into the atmosphere. Entire islands were battered by waves and ashfall. Communication cables snapped beneath the sea. That eruption transformed scientific understanding of submarine volcanic hazards. For decades, underwater volcanoes were often viewed as naturally suppressed by the immense pressure of the ocean above them. The Tonga event shattered that assumption. Scientists observed how shallow submarine systems can become exceptionally explosive once magma rises close enough to the surface for seawater and volcanic gases to interact in unstable ways. The violent expansion of steam, trapped gases, collapsing rock, and displaced seawater can create chain reactions powerful enough to send shockwaves around the globe. The developing activity in the Bismarck Sea appears far less explosive for now, but several details have raised concern among volcanologists monitoring satellite data. Thermal imagery suggests large amounts of extremely hot material are already approaching shallow depths. Steam-rich plumes indicate vigorous interaction between seawater and magma near the surface. Pumice rafts stretching across the ocean point to substantial fragmentation of volcanic rock. Some observations have hinted that a growing underwater platform may already be building upward toward sea level. One of the most troubling complications is the lack of precise seafloor mapping. Researchers know remarkably little about the exact structure of the eruption site. Existing bathymetric surveys in the region are limited and in some areas decades old. Modern high-resolution sonar coverage remains incomplete across large sections of the Bismarck Basin. That uncertainty matters enormously because eruption behavior changes dramatically depending on depth. A vent located several hundred meters underwater may remain relatively contained. A vent approaching shallow depths, however, can enter an unstable transition zone where seawater flashes instantly into steam and amplifies explosive force. The geological setting itself adds another layer of complexity. Northern Papua New Guinea sits along one of the most tectonically active regions on Earth. Multiple crustal plates converge, spread apart, grind sideways, and dive beneath one another across the southwest Pacific. The Bismarck Sea contains both spreading centers and subduction-related volcanic systems. Fault lines intersect beneath deep water. Magma pathways twist through fractured crust. Earthquakes frequently ripple through the area, sometimes triggering submarine landslides capable of producing local tsunamis even without a major eruption. Unlike towering volcanic mountains visible above the ocean's surface, submarine volcanoes hide most of their structure underwater. Their growth can proceed unnoticed for years. Pressure builds silently beneath kilometers of seawater. Gas accumulates. Magma chambers expand. New vents fracture the seabed. By the time visible plumes reach the atmosphere, major geological changes may already be underway beneath the ocean floor. Satellite observations from May 15th showed long bands of floating pumice extending southwest from the eruption zone. Such pumice forms when gas-rich magma cools rapidly after violent fragmentation. Large pumice rafts have historically accompanied powerful submarine eruptions around the Pacific basin. These floating volcanic rocks can drift for months across open ocean, disrupting shipping routes and signaling substantial eruptive output beneath the surface. The eruption has also revived concerns about how quickly underwater volcanic systems can evolve. The Tonga volcano that exploded in 2022 had already been active for years before reaching catastrophic intensity. Earlier eruptions in 2014 and 2015 created a temporary island between older volcanic remnants. Satellite imagery tracked the island's growth and erosion over time. Then, in January of 2022, the system underwent a dramatic escalation that obliterated much of the volcanic structure and carved an enormous underwater crater. Researchers later discovered that the eruption displaced immense volumes of rock, ash, and sediment while releasing atmospheric pressure waves that circled the planet multiple times. Tsunami waves propagated across the Pacific at remarkable speed. Scientists studying the event concluded that atmospheric shock waves themselves helped generate additional tsunami activity, amplifying coastal impacts far beyond the immediate eruption zone. Those findings transformed tsunami risk assessments associated with submarine volcanoes. Traditional tsunami models focused heavily on earthquakes and landslides. Tonga demonstrated that volcanic shock waves, collapsing eruption columns, crater formation, and rapid water displacement can all interact simultaneously during a large submarine explosion. The result can be a far more complex and wide-reaching hazard than previously understood. In the case of the Bismarck Sea eruption, authorities remain cautious, precisely because so many unknowns persist. Satellite imagery alone cannot fully determine the geometry of the magma system beneath the seafloor. Researchers still do not know the exact dimensions of the vent complex, the depth of magma storage, or the likelihood of structural collapse beneath the volcano. The current activity may remain moderate and short-lived. Historical eruptions in the region have varied dramatically in duration. One nearby eruption in 1957 reportedly continued for nearly 4 years, while the 1972 event lasted only 4 days. The possibility of a new island forming has attracted scientific interest, but island formation itself can introduce additional instability. Newly emerging volcanic cones composed of ash and fragmented rock are often structurally weak. As magma rises closer to the surface, interaction with seawater can intensify explosivity. Crater walls may collapse into the ocean. Explosive fragmentation can accelerate rapidly once vents breach shallow depths. Entire sections of newly formed volcanic structures can disintegrate during major eruptions. That process played a central role in the Tonga disaster. Before the climactic explosion, the volcano had built a substantial cone linking older islands. When the system destabilized, massive portions of the volcanic edifice collapsed into the ocean, contributing to enormous water displacement and tsunami generation. Geologists monitoring the Bismarck eruption have pointed out that the tectonic environment differs from Tonga in important ways. The current activity appears associated partly with a volcanic ridge near a spreading center, settings generally linked with less explosive eruptions than large subduction zones stratovolcanoes. Yet even moderate submarine eruptions can become hazardous if magma reaches shallow enough depths or if unstable sections of seafloor collapse unexpectedly. The Pacific region holds a long history of deadly volcanic tsunamis. Krakatoa in 1883 generated waves that killed tens of thousands after enormous volcanic explosions, and caldera collapse displaced surrounding seawater. Anak Krakatau produced another destructive tsunami in 2018 after part of the volcanic flank collapsed into the Sunda Strait. In Japan, the eruption of Unzen in 1792 triggered a catastrophic landslide and tsunami that killed thousands. These disasters revealed how volcanic hazards often extend far beyond lava flows and ashfall alone. Submarine volcanoes are especially difficult because warning signs can remain hidden beneath the ocean. Seismic swarms may be the only early indicator. Water discoloration and steam plumes may appear suddenly once activity intensifies. Remote locations complicate monitoring efforts. Ships cannot always safely approach active vents. Aircraft face ash hazards. Deep water pressure obscures direct observation of eruptive processes. Modern satellites have therefore become essential tools in tracking underwater eruptions. Instruments aboard NASA Aqua, Terra, Landsat, and PACE satellites have provided detailed imagery of the ongoing Bismarck activity. Infrared sensors can identify thermal anomalies through cloud cover. Ocean color instruments detect chemical changes and suspended material in seawater. Radar satellites may eventually help map newly emerging landforms if volcanic structures rise above sea level. Even with advanced technology, large uncertainties remain. Scientists still debate how close the vent may already be to the ocean surface. Some observers examining available bathymetric data have suggested existing charts may significantly underestimate the height of underwater volcanic structures in the area. The broader regional context also matters. Papua New Guinea ranks among the world's most volcanically active nations. The country contains dozens of active and potentially active volcanoes spread across island arcs and submarine ridges. Several major eruptions during recent decades have displaced communities, disrupted aviation, and triggered evacuations. Coastal populations throughout the region remain vulnerable to both volcanic hazards and tsunamis due to their proximity to active tectonic boundaries. The Bismarck Sea itself serves as a critical maritime corridor linking Pacific trade routes and regional fishing grounds. An escalating submarine eruption could affect shipping through ashfall, floating pumice, reduced visibility, and hazardous swells. Large pumice rafts are capable of clogging ship intakes and damaging vessels. Ash clouds threaten aircraft engines. Tsunami risks, even localized ones, create serious danger for coastal settlements and marine traffic. Environmental impacts may also spread far beyond the eruption zone. Submarine eruptions inject massive quantities of minerals, volcanic gases, and ash into seawater. Marine ecosystems can experience abrupt temperature changes, reduced oxygen levels, and altered chemistry. Fish migrations may shift. Coral reefs can suffer burial beneath volcanic sediment. At the same time, volcanic material sometimes enriches nutrient levels that stimulate plankton blooms and temporarily reshape marine food chains. Researchers continue examining how the Tonga eruption altered atmospheric conditions after injecting enormous amounts of water vapor and ash into the upper atmosphere. Some studies suggested the event produced measurable climatic and atmospheric effects on a global scale. For coastal communities across the Pacific, the memory of Tonga remains vivid. Video footage from 2022 showed tsunami surges sweeping through harbors, flooding streets, and carrying debris inland. Communications outages isolated islands for days after undersea cables were severed. Ashfall contaminated drinking water and disrupted transportation. The eruption demonstrated how a remote submarine volcano could generate consequences felt across an entire ocean basin. That memory now shapes reactions to the unfolding Bismarck Sea activity. While there is no indication at present that the eruption is approaching Tonga-scale intensity, scientists remain wary of making definitive assumptions too early. Volcanic systems can evolve rapidly. Magma pathways may shift unexpectedly. New vents can open. Structural collapse may occur with little warning. The eruption's current stage appears dominated by steam-rich emissions, floating pumice production, and moderate ash release. Yet the transition from relatively stable submarine activity to highly explosive behavior can occur when specific physical thresholds are crossed. Water depth, magma gas content, vent geometry, and eruption rate all influence explosivity. If magma accumulates beneath a partially sealed vent system, pressure may increase significantly before sudden release. The ocean itself becomes both suppressor and amplifier in such eruptions. Deep water pressure can inhibit gas expansion initially, but at shallow depths, seawater contacting hot magma flashes instantly into steam, expanding violently and fragmenting surrounding rock. That interaction can create chain reactions where explosive fragmentation exposes more magma to seawater, intensifying the eruption further. In Tonga, those interactions ultimately produced a blast heard thousands of kilometers away. Atmospheric shockwaves circled the globe multiple times. Barometric disturbances were recorded across continents. Tsunami waves reached shorelines throughout the Pacific Basin and beyond. The current eruption in the Bismarck Sea has not displayed anything approaching that scale. Still, volcanologists emphasize that submarine eruptions remain among the least predictable natural hazards precisely because direct observation is so limited. Many underwater volcanoes have never been mapped in detail. Some remain undiscovered entirely until eruptive activity disturbs the ocean's surface. NASA scientists monitoring the event noted that researchers possess more accurate topographic data for parts of the Moon and Mars than for sections of Earth's deep ocean floor. That reality highlights a major vulnerability in global volcanic monitoring. Critical geological processes capable of generating tsunamis, atmospheric shock waves, and new islands may unfold in remote ocean basins with minimal direct instrumentation. For now, the eruption continues under close observation from orbit. Satellite images reveal expanding plumes and persistent thermal signatures. Ocean currents carry pumice across the sea surface. Clouds of steam and ash intermittently obscure the vent area. Beneath the waves, magma continues forcing its way upward through fractured crust along the Titan Ridge system. Whether the eruption ultimately fades after days, continues for months, or evolves into a more dangerous phase remains uncertain. Geological history across the Pacific has shown repeatedly that underwater volcanoes can remain deceptively quiet before escalating with astonishing speed. The Pacific Ring of Fire contains thousands of submerged volcanic structures, many capable of producing powerful eruptions under the right conditions. The developing situation north of Papua New Guinea serves as another reminder that some of Earth's most powerful geological forces remain hidden beneath the ocean's surface, largely unseen until steam, ash, and waves finally reveal their presence. Across the Western Pacific, monitoring agencies continue watching the Bismarck Sea carefully, aware that beneath those dark waters lies a volcanic system still writing the next chapter of its eruption in real time. Far beneath the shipping lanes and fishing grounds of the Western Pacific, the geological forces driving the Bismarck Sea eruption continue operating inside a region shaped by relentless tectonic movement. The area sits near the boundary where fragments of Earth's crust are constantly colliding, spreading, and grinding past one another. That instability feeds a chain of volcanoes stretching across Papua New Guinea and neighboring island arcs, many of them hidden below the ocean surface. Scientists studying satellite imagery and seismic records have noted that submarine eruptions in such tectonic crossroads can evolve unpredictably because magma may migrate through multiple fractures rather than a single volcanic conduit. In practical terms, that means activity observed at the surface may represent only one portion of a larger underground system still reorganizing beneath the seabed. The danger associated with underwater eruptions is not limited to a single explosive event. Prolonged volcanic activity can weaken sections of the seafloor over time, increasing the possibility of underwater landslides capable of generating localized tsunami waves even without a massive blast. Volcanic ash and fragmented rock accumulating on steep submarine slopes may eventually collapse under their own weight. In regions where coastal communities sit only a few meters above sea level, Even moderate tsunami surges can become destructive. Low-lying islands and shoreline villages across Papua New Guinea and nearby Pacific nations remain especially exposed because many communities depend directly on coastal access for transportation, fishing, and trade. Researchers monitoring the Bismarck Sea eruption are also paying close attention to ocean temperature patterns surrounding the vent area. Thermal anomalies detected by satellites indicate large amounts of heat are being transferred into surrounding seawater. In major submarine eruptions, those temperature changes can alter local marine conditions rapidly, affecting fish populations and disrupting fragile reef ecosystems. During previous Pacific eruptions, floating volcanic debris fields spread across enormous distances, at times reaching coastlines thousands of kilometers away. Ships encountering dense pumice rafts have reported engine damage, blocked cooling systems, and navigation hazards, severe enough to force route changes across sections of the Pacific Ocean. Another factor adding uncertainty is the possibility of multiple eruptive phases. Some submarine volcanoes experience cycles in which explosive activity subsides temporarily before intensifying again as fresh magma rises upward. Short, quiet periods can create a false impression that danger has passed when underground pressure may still be increasing. The Tonga eruption in 2022 followed earlier eruptive episodes that appeared comparatively limited before the volcano entered its catastrophic phase. That history remains central to why authorities and scientists are treating the Bismarck Sea activity with caution despite the absence of any extreme explosion so far. For now, satellites remain the primary window into a volcanic system hidden beneath turbulent waters north of Papua New Guinea. Each new image adds another piece to a puzzle that is still far from complete. Steam plumes, drifting pumice, expanding thermal signatures, and changing ocean color patterns all point to an active geological process continuing below the surface, where pressure, magma, and seawater remain locked together in one of nature's most volatile environments.